Bismillahirrahmanirrahim. We had completed the yield criteria before disruption of academic activities, and I'll just summarize that here. For yield, we had compared two quantities. One was some sort of a stress parameter, and the other was the yield strength of the material. And because we didn't want the component to yield, we made sure that the stress was less than the yield strength. Symbolically, parameter with stress should be less than the yield strength of the material. Obviously, we are talking about design, so we don't want the stress parameter to go anywhere near the yield strength. So for design, we had used this using the factor of safety, or if we can say, if we define allowable strength to be the yield strength divided by the factor of safety, we could write it like this. Now, the precise shape of this stress parameter could be different according to the yield criteria. For example, for von Mises criterion, it was something like these are all principal stresses. And obviously we had similar expressions, somewhat different expressions, but expressions in terms of principal stresses for the case of the maximum shear stress theory. So without going into the details, this is what we had done. Now it's tempting to think that if one takes care of avoiding yield, one should be all right as far as the strength-based design is concerned. But that would be a mistake, because as discussed in the introductory part of the course, yield is just one factor to consider here, because it's possible that the material, although it is ductile, fails in a brittle manner without undergoing general yielding. The nominal stress level at that time will therefore be even less than the yield strength of the material, and obviously there will be no warning before the breakage. And why this happens? This happens because there is sooner or later all the components will have cracks in them, and it could be that for a certain combination of crack length and the applied stress, the component breaks in a brittle manner. So all this can be called ductile. When we are talking about failures, this is ductile failure. But when we talk about brittle failure, that without a warning, we need to find out how that happens. So first of all, here you cannot ignore stress concentration. We had talked about, when we talked about yield criteria, we said that for different reasons, we could ignore stress concentrations, but not here. They play a big role here. So let's see how brittle failure occurs without warning, without undergoing yielding, how a material can break. Let's start with taking an infinite plate. Now this is a very favorite thing among the people who do theory of elasticity. This taking of an infinite plate, very big plate. Nothing is infinite in life, but it's very big. The dimensions of the plate are big as compared to the crack length. It makes mathematics easier. So it's always good to start from an infinite plate. Obviously, in real life, we'll be dealing with finite plates and we'll see what we do about them. But if such a plate is subjected to a far field stress of sigma, and this length of the crack is 2a. This is also a tradition. We don't take it a, we take it 2a. It will become clearer when we move forward. And we are interested in finding out the stress at this point, a distance r away, and at theta, at an angle of theta from the positive x-axis. We never forget to write the coordinate axis. Without these, what what will follow will have no meaning. So the theory of elasticity solution for this problem, the stress, and in this case the predominant stress, the most important stress will be stress in the y direction. It comes out to be I've not written the complete solution, it's a bit longer, but for the first approximation, this is a comparatively accurate solution. Now, this gives us the stress level at any point in a plate which is subjected to this kind of loading. Now, there are different stresses for different plates. There are different crack lengths. So you cannot hope to get one expression for that. And that is why we have this K. This K will be different for the different configurations. By configurations, I mean stress levels and length of crack. And this K is something that characterizes a particular crack. Now, we'll discuss more about this K later on. Now, let's take an angle theta is equal to 0. What happens at theta is equal to 0? From these expressions, we can see these cancel out. So what we get is sigma y becomes, so 0 means we are talking about this line now. Now, as we move on, what happens as we reduce this r to 0? And it's an interesting question because you put r equal to 0 here and you get an undefined stress here. Some people call it infinity, but actually it's undefined, because for any crack length, for any applied stress, it gives you the same answer, undefined. So it's not much very useful. So this K, we need to find out what happens with this K here. So for r is equal to 0 at the crack tip, the stress becomes undefined. So we cannot characterize the smallest or the largest crack length, because both will give us the same situation, that is sigma y is equal to 0. So as far as the mathematics is concerned, all cracks are of equal gravity, which is not very useful for us. So we take a different route. What do we do? What do we know about the stress sigma y? Two things we know. Number one, sigma y will be proportional to the applied stress level. We don't know the constant of proportionality, but it will be proportional to sigma. That we know. The higher the sigma, the higher should be the stress levels here. And what about the other thing? What about the crack length? Again, it's obvious, the bigger the crack length, the bigger the crack, the higher should be the stress here. How do we know that? For that, we need to consider the stress trajectories. Let's consider them here. Let's take a plate without any crack whatsoever. Here it is subjected to a far field stress sigma as before. So how the stress transmits from one point to the other? Just straight lines. It's just a schematic. So the stress lines are straight. They don't have any obstruction in them, so there's no problem. Now take another case, the second one. Here we have a very small crack. Same far field stress sigma. Here what happens is these trajectories don't have a problem. These trajectories don't have a problem. What about these? Obviously there's no material here, so they have to pass like this. What about these? Again this. So all these which are disturbed by the crack, they get diverted, and there is a very sharp concentration here of stress. Now what happens in case of a bigger crack length? Now this was small crack, this is a big crack. Obviously more trajectories will be diverted in this case, many, and obviously these are in the millions. So you get a higher stress here, lower stress concentration. Here you have higher stress concentration. So obviously the stress here, we're talking about the stress at sigma y at this point, it has to be a function of the crack length also. So starting from continuing from our consideration, this was dependent on sigma, and this is also dependent on sigma y, also depends on a. But does it depend on a, or it depends on a square or under root of a? We have to see this, because this has a unit of MPa or Pascal, whatever. The right hand side should also have the units of MPa. But here we have this MPa is this alone. Now, if this is in meters or millimeters, then we have another dimension r, which is also in meter, but it is an under root. So to cancel this unit, it should be obvious that the stress should be proportional to not a but the square root of a. Now if we remove the proportionality symbol, and we have to introduce now a constant of proportionality. So this is the situation here. C is a constant. Now what is the value of C? It needs a very rigorous analysis to calculate C, but and that is outside the scope of our work here. Let's say that for this case, infinite plate, C turns out to be under root of pi. For this case alone, we'll talk about the other cases as they come along. So we can write this whole thing as now what was the original expression? The original expression was sigma y is equal to k 2 pi r, and now we have reached this solution. So equating these two terms, it would appear that k turns out to be, for this infinite plate with the center crack, it turns out to be let me write here very clearly that this is for infinite plate and with a center crack. Now, plates, there can be other forms of plate, obviously, other forms of cracks. For example, it could be an edge crack. It could have been here. So we are talking about center crack. When we encounter edge cracks, we'll see what we do with them later on. Now, this K is called the stress intensity factor. And its units will be, as you can see from here, they will be something like or depending on the situation, whatever, this sort of thing. So this is different from the stress concentration factor that you have been using, which is obviously dimensionless. Now let us take one more step. You will often see this K expressed as this K1. You'll see in your textbook also. You'll be dealing with K1 a lot, not K but K1. Now this K1 is nothing, it just means this is the mode of loading, because there are different modes of a plate loaded with a plate with a crack which is loaded, and so there can be different kinds of loading. For example, we have just seen this sort of this is what we are considering here. This is called mode 1, and it is also called opening up mode. Now the same plate could have been loaded in shear, and this is called mode 2. The same crack, same plate, but now the loading is different. This is called mode 2, and in other words, sliding or in plane shear. Also, same crack. The shear could be something like this, out of plane. This is called mode 3, and it is called tearing or out of plane shear. So this one only tells you what kind of loading is there. So for our purposes in this introductory course, we'll only be dealing with K1, and K1 is the most predominant, most frequently occurring mode. And even in cases where you have mode 2 and mode 3 mixed with K1, ultimately the crack proceeds in such a direction that ultimately it becomes K1. So if you can deal with K1 for now, it should be enough. Now here, one of the important things to consider here is that this sigma, this when we talk about the stress, sigma is the far field stress, what we will deal with, not the stress here, because here the stress tends to be very high. It's not always easy to calculate what it is, and we don't need to do that. We deal with the situation, the severity of the crack here, by considering the length of the crack and the far field stress, the stress which is far away from this point, which is very easy to calculate. So this should be kept in mind. Now, what about the question that we postponed some minutes ago? What happens when the plate is not an infinite one? Obviously, in practice, all plates will be finite plates. And what about the other configurations? For example, there could be, this is a center crack, there could be a crack like this, and these are more dangerous cracks because they tend to run away easier, the edge cracks. What happens when we encounter an edge crack or a center crack, but the dimensions of the plates are different. Or what happens, for example, that when there is a pressure vessel, I'm just showing the cross section, and there's a crack here, and obviously there's pressure inside, so tends to open up. So K1 will be valid, but now the crack is not a thin plate or a thick plate for that matter. It's a pressure vessel. What happens here? Or the crack could be here. So there'll be different configurations in real life. What do we do when we encounter these situations? Very simple. This K1 becomes not sigma pi a, but here there's a constant beta. Now this beta will again be different for the different cracks that you encounter. And where do we get these betas from? We have convenient tables, and we in your textbook also we have them. Theory of elasticity deals with them. Finite element analysis can be used, but we won't go on calculating these B's for any situation we encounter. We'll just look up the values from some table. Now we come back to this K1, which we'll just hold it here, and we have to see why does a plate or a component just break without any warning. We expect that when you pull a tensile test specimen, for example, a tensile test specimen, and you keep on pulling it, there comes a time when it yields, and then there's a neck, and there's a considerable deformation here. You can even at the end you can see the deformation, and ultimately it will break into two. That kind of thing is expected. But if there is a component which is made of a ductile material and it just breaks without any warning, without any plastic deformation, what happened? We have to consider the energy considerations here, because only stress may not be enough to explain this. Now what happens is that if there is a plate here and there is a stress here, when does this crack extend? There must be some situation, some condition that is satisfied for this crack to extend, or it remains the same. So it has been found out that the energy required to extend this, obviously there's plastic work done at the tip of the crack as it extends. It takes a lot of energy. Now this energy comes from the unstraining of the material that has extended. This, if this crack extends from this point to this point, then this region was stressed, but now it's not stressed anymore because it has the crack has extended, so the energy has been released. Now this same energy, the energy released, pays for the extension of the crack. Now when will the crack propagate? When this energy release rate, energy release per unit crack extension, is sufficient for the energy requirements to make this additional crack. So there are two things: energy release rate and the energy required to create the crack, the new portion of the crack. Now it happens that the energy release, it is a quadratic function of the crack extension, and the energy requirement for the formation of a new crack, it is a linear function of crack extension. Let's say this is crack, and the increments of cracks are delta A. So if you want to increase the crack, the energy needed will be a linear function of delta A. This is energy needed, and energy released from the portion of the plate which was stressed, but the stress was released because of the extension of the crack. There cannot be any stress anymore here because the crack has extended. That energy released, it's a quadratic function of crack extension. Now this is the energy requirement, this is the energy available. If you superimpose the two, you get something like this, which shows you that for a certain level, for a certain crack length, and we'll call it AC, critical crack length, you need to put some work in order to extend the crack. But once you reach this point, or in other words, you have a crack length which is equal to or greater than the critical crack length for this stress level, for a particular stress level. For a different stress level, the critical crack length will be different. For this, for the stress under consideration, if you have a crack of length AC or more, then it's a spontaneous crack extension. You don't need to, you need extra work to increase the crack length. So this is what happens when a critical crack length is present in the component somewhere. Then for that stress, if you apply that stress, that should be enough to extend the crack uncontrollably, because the energy available by extension, the energy released by the extension, will be more than enough to pay for the extension of the crack. So this is what happens. So how do we know if a certain K1 value, which we can calculate by this, if we know the crack length, we know the sigma, whatever the sigma is. How do we know if a certain stress intensity factor is enough for the crack to run away uncontrollably? It's very simple. Just like in the yield, we compared the stress parameter with the material property, the material property being yield strength in that case. Here we will consider K1 to something called K1C, which is critical stress intensity factor, and this critical stress intensity factor, or sometimes called fracture toughness. If this K1 for any situation becomes equal to, if it's less than the K1C, the crack will not run away, so it's safe. But if it is equal to K1C, it will not give you any warning, it will just break. Now we come to the critical question of how to know K1C of a material. How to know what K1C is for a particular material. The answer is simple. How did we know what the yield strength of a material was? Obviously, we went to the lab, we pulled a specimen to yield, and we measured that. Similarly, we know the form of this K1. The form of this K1 is, we can take a plate, put a certain A value. Actually, what for a center crack we use a value of 2A, and I'll discuss this point a little later. But for calculation, we'll always take A. Put a crack of length, we call it a length A. For center crack, it becomes 2a. For a edge crack, it will become a. Center crack is nothing but, you can say, two edge cracks combined, although it's a benign form of edge crack. For example, a crack under the same load sigma, edge crack, and a center crack with the same load sigma. The center crack will be 2a length, the edge crack will be a length. They are equivalent, but obviously this is slightly benign. The stresses here will be slightly less, and I'll leave the students to think of the reason why. There's similar results. The stresses here will be similar, but this will have slightly more stresses, and this has more ability to run away. In other words, the beta for this will be higher than the beta for this one. Now coming back, it's very easy to find out the critical stress intensity factor. You just take a plate, put any crack length in it, and then start pulling. At a certain sigma, it will start running away. Before that, it will be stable. At a certain sigma, it will run away. The crack will extend uncontrollably. And then you know that at that point, the energy release rate was higher than the energy required to increase the length of the crack. Because before that, it was not extending, now it extended. So at that point, this will become sig, and this A will become AC. So when you use a certain crack length, put in the value here, and for the stress that makes this crack run away, put the value here, and whatever you get here will become the critical stress intensity factor. Now, this is all we have here as far as the brittle fracture of ductile materials is concerned. Obviously, there is a long story behind all of these things that we have considered. You can go deeper and deeper into it, but this is the gist of it. And for our practical purposes, this should be enough. We know how to calculate the stress intensity factor, and we know what to compare it with to know whether a certain component is safe from the point of view of brittle fracture or not. So we leave it here. In the next video, we'll apply these concepts to problems of the real world. Thank you.